Okay, well, let's get started. I hope everybody knows who Richard Feynman is. First of all, let me make sure that everybody uh, can somebody say something that they can hear and hear me and see
Yeah,
this.
we can
Hi, we
see
can
you. Yeah.
see.
Great. Okay. Um, so Richard Feynman, he got the Nobel Prize in Physics in 1965 for quantum electrodynamics. But also he was one of the greatest physics teachers. There's a set of three big red books on basically physics one, physics two, and a little bit more, that he looked at physics a little bit differently. He was also one of the fathers of nanoscience. Anyway, the story is that one of the professors here at Northeastern, when he was at MIT, he was at an old wooden desk, and he pulled out the bottom drawer, and evidently the bottom drawer was this set of papers. And so he pulled it out, and he noticed it was a lab report written by Richard Feynman in 1937. And well, anyway, you can see the whole report if you click on the down here on the far left. Anyway, he got an 85% grade on it. Okay, one of the brightest minds in physics. I just wanted to show you that. Okay, here we are, week 8. We're going to do optoelectronics, and then after that, today we're going to finish the lecture, and then you'll have the lab on Thursday and Friday, and that'll be the end of the analog electronics. And next week we're going to start digital electronics, and so we have lectures on Monday and Wednesday. Okay, so we'll cover digital basics and logic networks and so on. And then the week after that, pulsed ICs. That's important because pulsed digital electronics is all of our computers are based on that. And then the following week we'll have exam. That's the second exam. We will not have a final exam. And then there's Thanksgiving after that. Okay, so optoelectronics. It's just what it says. You have optics and electronics, and they're connected together. So we're going to look at communications, how that's used in fiber optics. And then we're going to look at just basically a little bit of about the light spectrum and vision. I thought that was just kind of interesting. And then we get to the physics of it, the spectral response of semiconductors. What is a semiconductor band gap? Very, very important for all of optoelectronics. It arises because of quantum mechanics. Then we'll look at the basics of light detectors, photocells, solar cells, photovoltaics, and light emitters, LEDs, laser. I won't go over the ruby laser. And then just a little bit about the lab, but you'll be able to see the lab even if you come in and do it. Are there any questions about what we're going to be doing in the next few weeks? Okay. How do we go from optical things to electronic things and backwards? Well, a lot of it uses semiconductors, light emitters. You're going from electricity to optics. You have LEDs. You can make things similar to LEDs, but they're laser diodes. And light bulbs now. White light bulbs are made with semiconductors. And look at light detectors, how you go the other direction, how you go from optics to electrical signals. So we're going to look at silicon photocells. You work with one of those in the lab today. And there's also other types of semiconductors that work at different wavelengths. But all of these things, all of these semiconductors have p-n junctions in them. They just wouldn't work without p-n junctions of some kind. Okay, what do we use some of these optoelectronics for? Well, here's an example of CD-ROM memory. They're becoming obsolete now. As solid state memory becomes higher and higher density, then older generations of things that have memories are being phased out. Well, I just wanted to show you this example of how it works because it's kind of interesting. So you have a plastic disc here, and it has a metal, very thin metal layer on the top, and it has pits in it. So this is like a phonograph record, and it has pits in the metal. And the way it works is you have a laser, like a red laser, or now you have blue lasers, and that sends a beam of light, and it's reflected by a half-silvered mirror, and is focused onto this rotating disc that's rotating at 7,000 RPM, very fast. And at each time a little bit comes by where there's a pit, the reflection coming back from that disc that goes again through this half-silvered mirror and then goes onto the photodetector. So the photodetector gets a different electrical signal each time a pit goes by. And then you can see you can have short pits, long pits, medium pits, whatever. Okay, so that's one way to store permanently on a disk. I think these things generally only last about 10 years before they start to degrade a little bit. Let's see if we can do this. Stop sharing. Where are we? Screen share.
Information in a computer is stored as thousands of zeros and ones called bits. On a CD-ROM.
Can you see and hear this?
Yep.
Yes.
Good.
Bits are represented by microscopic holes and bumps called pits and lands. When a laser beam is reflected off of these tiny hills and valleys into a photodiode, they turn into an electrical pulse that a computer recognizes as a stream of zeros and ones, thus recreating words, images, and sounds.
Okay. Sharing, share. Okay. So let's look at optical communications, such as Verizon, Fios. A little bit about the history of telegraphy. Communication over distances. Well, in ancient times, you could send a smoke signal. You could use lamps. Semaphores. Semaphores were flags that you'd hold up in the air. You could hold them above your head. You could put them to the right, to the left, put them down. And each one of those things meant something different. So somebody could see that over a number of miles, and you could communicate that way. Otherwise, you had to send somebody on a horse with a written message. So that was fairly important. And then came along electricity in the 1700s. That someone suggested, well, if you put voltage on one wire, that could be one letter. Well, 26 wires to send some information is not very good. And then along came, well, a number of people worked on codes where you could send information on one wire and that could be letters or numbers. And Samuel Morse came up with Morse code. And I guess I have to stop sharing and resharing each time, or can you see this?
No.
Right. Let's try this. Just holler if you can't see this.
Morse code was a method of transmitting textual information as a series of analog tones that could be directly understood by a skilled listener. Example. Hello world.
Okay, let's stop sharing this. Go back to here. Okay, you notice that the letter E is the most used letter in the alphabet, so he made that one dot. So I guess you know there's some more intelligence behind this that you know if you're going to send something, you want to have the most used letters have the least amount of time on. This is what I find very, very interesting here is in 1858, 150 years ago, they put electrical cable that went all the way across the Atlantic Ocean, thousands of miles that lays basically on the seabed, going from New York to London. I find that rather fantastic. 150 years ago that you were able to do that. And of course, you couldn't get a signal to go that far in a wire, so you had to have some sort of amplifiers in between. So that there was another technological issue that they had to overcome. Okay, so we went from optical to electrical, now back to optical. Even Alexander Graham Bell, the inventor of the telephone, was able to transmit some sort of information by light from, I guess, a light bulb in air. But it wasn't until we started getting semiconductor diodes, lasers, that we could send information in glass fibers. And the first system of fiber optics was developed around 1965. Any questions so far? Okay. Examples of optical digital encoding. Okay. If you're going to take any information, you have to put it into some digital numbers, you know, just zeros and ones. Okay, so here's this is a clicker, you know, that you use for your television or whatever. It has an LED in it, an infrared LED that you can't actually see. Your eye doesn't respond to that wavelength because it's about 800 or 900 nanometers, just outside of our visible range. So I took this myself and I grabbed a photodiode and a resistor, and then I attached that to an oscilloscope. So then I could press a button, and then I could see what sort of voltages were produced from this photodiode for each button I pressed. And here's what I got. So here's photodiode voltage as a function of time. Look at the scale; it's milliseconds. So this is a hundredth of a second, 10 milliseconds. So within a couple hundredths of a second, it sends this information. So when I press 0, it put out these optical pulses. First, there was a long initial pulse, and then long, short, short, long, short, short, long. And so you could write this as a digital number. If you're going to say a long is a 1 and a short is a 0, then you'd have this digital number for pressing 0 on the clicker. And then for these various numbers, I collected this data on the scope. By the way, the voltage was between 0 and about a half a volt, and I just for the different numbers, I just raised them up so they wouldn't lie on top of each other. But you can see each different number has a different each base 10 number has a different binary number. Okay, so this is a way to transfer numbers into digital, or you could do letters too. You can transfer letters into digital. This is just an example. Any questions? Yeah, notice that I had to put a resistor here in parallel across the diode, and we'll get to why we do that. Okay, so let's look at optical communications. You have some information that's voice, video, whatever. You convert that to digital information, then you send some sort of pulses, because you don't want to send analog information. That is, you don't want to send the number 1 is 1 millivolt, the number 2 is 2 millivolts, well, something like that. So you don't want to have different heights of, say, optical heights. Certain number of photons is a 0, more photons is a 2. You want to have that as just on or off, okay? Zeros or ones. And then, so you start off with a coder, get pulses. Then you have a detector that changes those pulses. These are electrical pulses, by the way, and that's changed into optical pulses. And the optical pulses go through this optical fiber. They hit a photocell and then come out as electrical pulses. And then you decode that back into the original voice or video. So you have input data, some circuitry goes to light, that goes through a fiber, that goes to a detector. That detector turns the light back into electricity, and then to digital information, and then finally you decode that. So here you have electrical to optical. You send the optical, and then you take the optical and you convert that back to electricity. Okay, two-step process, just a mirror image. Okay, so you can see that you have information going through this optical fiber. In the systems we're using now, they use a semiconductor laser diode. They use it at a wavelength of 1.55 microns, which is in the infrared. You can't see that. It's outside the visible range. But that is where glass fibers have the least absorption. So you can transfer much, much farther if you use this particular wavelength. That's kind of the standard wavelength. So in a system that has, say, 10 gigahertz, the pulses, they're only a few centimeters in length. Okay, so the optical pulses, if you could look at them as they travel in space, they would only be a few centimeters long. Okay, these are basically picosecond long pulses. And the fibers are made of glass, optical glass, SiO2, also called silica, also called amorphous quartz. and they have a very small core diameter. So you're sending all this information in a very tiny cross-sectional area of less than 10 microns in diameter. Very small, very small. Okay, and then the detector, the gallium indium arsenide phosphide laser produced the light, and then the indium gallium arsenide photodiode detected the light. So let's just quickly go over the optical fibers. An optical fiber here, here's the core, and then you have to have a cladding around it of a material that has a smaller index of refraction. And then you have some buffer that just makes it stronger. So the nice thing about an optical fiber is if you put light in at an angle that's, that's roughly along the length of the fiber, it will get trapped in there by total internal reflection. So in this one, you can see that light, even though it's bouncing off inside this curved fiber, it will stay in that fiber. Okay, I'm pretty sure you've all seen these things that set on your table that have 100 fibers sticking out, and you can see a little bit of light coming out of the end of each one of those, but you don't see any light coming out of the side of them hardly, because not much leaks out. And it's because you have total internal reflection. And the way you do that is that the cladding layer, that's this cladding that goes around the fiber, has to have a smaller index than the core region. I mean, you can see that here in this middle picture. So if the cladding has a lower index of refraction, you get total internal reflection. Otherwise, it would just go out. Okay. Okay, let's look at improvements in fiber optic communications. So the first transatlantic wire cable was 150 years ago, and then the first transatlantic cable was roughly 50 years ago. And it costs pretty expensive, right? $30 million to lay a cable. The time of each pulse to cross the Atlantic from New York to London is only 50, 70 milliseconds. So you can send lots of pulses just in 1 second. Note that either in optics or electrical signals, sending them thousands of miles, you have to have repeaters of some kind or some sort of way to amplify the signals. And they do that in fibers. Here's a typical loss in an optical fiber, 4% per mile. So maybe you could lose 99% of the signal and still see it. Well, that's going to be lots of miles before you have to have a repeater. Okay, one last thing about optical communications. We're all interested in sending more information faster, especially video. As video, your televisions now are, 4,000 pixels. You're getting more and more pixels, more and more information all the time, higher resolution. So you need to be able to transfer information faster and faster. So how do you do that with optics? Okay, it's called wavelength division multiplexing. Okay, here's a video. Let me show you that.
Hello everyone, this is Colin from Fiber Optics for Sale. In this video, I will explain what is WDM uses this same idea. Traditionally, only one colored light was used on a single strand of fiber to carry the information, such as 50-50 nanometer light. However, starting from the early 1990s, the internet boom pushed service providers to find a method to increase the capacity on their network in the most economical way. That is when WDM devices were invented. As shown in the right side picture, in a WDM system, many different colored lights are combined by a WDM multiplexing device and put into a single strand of fiber. Each color is called a channel. On the receiving side, each color is separated into its own channel by a WDM demultiplexing device. It shows that a single fiber's capacity is increased by 40 times with a 40-channel WDM. The beauty of WDM is that you only need to upgrade the end equipment. No need to dig up trenches to carry more fiber, which is much more costly. So,
Okay. Okay, so that's what's nice about optical fibers is you don't have to use just a single laser at a single wavelength. You can have multiple wavelengths transmitting that don't couple with each other. So if you have something in the blue and something in the red, different wavelengths, those wavelengths, the electromagnetic radiation will not couple to each other. So they're separate, and then you can separate them eventually later. So here's a plot. I think it's kind of interesting. This is the rate of transmission of information. So this is gigabits per second, and this is terabits per second as a function of a year. So down here, this data is for a single wavelength, and then this data up here is for multiple wavelengths. So two things to notice in this. If you look at, they're always getting a higher signal in research. Research means, in a laboratory, you can transmit so many gigabits per second of information, but then the actual product that you sell lags behind by roughly 10 years. So it's about a factor of 3 or 4 difference in the rate here at a given year, but it takes almost 10 years for the product to catch up with what research is. The second thing you can notice is if you look at, say, the product line here, this blue one for wavelength division multiplexing, and the product here for a single wavelength, the difference here is about 100. But this is on a log scale, so 100 would go from here up to here, from 100 gigabits per second to 10 terabits per second. So that means that these products here have about 100 different wavelengths in each fiber. Okay. Okay, so in summary, advantages of optical over wire: higher bandwidth, much higher bits per second, especially when you send different colors of light through a fiber. Glass is less expensive than copper, especially if you're sending it, hundreds of miles. And you need much smaller cables to do this. It's more energy efficient too. Okay, any questions on optical communications? Is everybody with me here?
I have a hopefully quick question.
Sure, yeah.
When you were talking about how they used like multiple different wavelengths and color, not colors, but kind of, I guess, to
Yeah.
send many different to have multiple channels in a single wire. You said they
Mhm.
don't. You said that the radiation doesn't couple with each other. Why don't they couple with each other? Because wouldn't they like have to have similar wavelengths if they didn't want to like hit that um
Yeah.
that range where the glass fiber has the least absorption ratio? And like, wouldn't they
Well,
interfere with each other?
yeah, so um, the the sort of the average wavelength is 1.55 microns wavelength, but that's split into just a very, you can split it into very finely. So maybe the difference is goes from 1.54 to 1.56 microns. That just over that very small range, they can divide that up into a whole lot of different wavelengths. So it's still within the low absorption band, but I believe, I don't know what the exact range is, but it's not very far. It's not very far off. That maybe maybe the difference from one wavelength to another, well, it's certainly less than 1%. It's maybe less than 1/10%, even in the wavelength. So the wavelength is the difference in wavelength is very small. The second thing is light is not going to cross couple with each other, like one color, one wavelength going through and another going through and a second one going through. The second one isn't going to affect the first one. I mean, there are things called, there's a whole field of nonlinear optics in which you can couple two different wavelengths. I did some experiments on that when I was a graduate student. But that needs very high intensity lasers to do that. Lasers that would burn holes and things, basically. So at these kind of powers that they're talking about, powers or intensities, are low enough where the signal at one wavelength is not going to affect the signal at another wavelength. Yeah.
All right, thank you.
Okay. Any other questions? Okay, I just thought, this was interesting because there's a lot of physics and engineering that goes into optical communications. Okay, briefly, let's just go through the electromagnetic spectrum. I won't spend that much time on it. The whole electromagnetic spectrum, like radio waves, the same as gamma rays, but they're just different wavelengths. And if you look at what our visible spectrum is just a tiny, tiny sliver of the total electromagnetic spectrum. I mean, you can see up here, well, let's look down here, wavelength, 10 to the 6 meters for radio waves, 10 to the minus 16th meter wavelength of gamma rays. Okay, that's 22 orders of magnitude. Yet the visible spectrum doesn't even span a factor of 2. Blue light is about 400 nanometers and red light's about 700 nanometers. Okay. And this is basically, well, we'll get to that. So this is the wavelength of the visible spectrum. But in physics, the units of electromagnetic radiation, we usually refer to what's the photon energy. What's the in the particle wave duality of physics, we say that radiation can be wave-like or it can be like a particle, and we call those photons. And those photons can have an energy. We call that an electron volt. And that energy is just the energy that if you accelerated an electron with 1 volt of potential, that would be, it would gain a kinetic energy of 1 electron volt. Okay, so that's what we usually use in physics. You know, when you talk about GeV or TeV and a particle accelerator, they're using photon energy. In semiconductors, we'll use milli-electron volts or just electron volts. You can also talk about color temperature too. So all substances emit electromagnetic radiation according to their absolute temperature. I mean, this is just physics. You should have had this in physics too. So here's Planck's law here, and you can calculate the amount of radiation power as a function of this is frequency here, but you can plot it in terms of wavelength. So I just made a plot here of this equation, and here's the sun, the temperature of the sun, the surface of the sun, by the way. The interior of the sun is millions of degrees, but we're lucky that the surface of the sun is much cooler, because otherwise we'd be basked in X-rays hitting the Earth. Anyway, so if you just take the surface of the sun's temperature of this, you get a plot like this. It peaks. The sun has a peak and right at the visible. That's not a coincidence, okay? So an ultraviolet is a shorter wavelengths and infrared is a longer wavelengths. So that's the sun. If you take white hot, like a light bulb, say 2600 Kelvin, you get a peak like this. So you get almost no blue light. You can see the intensity near blue is very, very small. But there's still enough blue, so it adds these 3 to give you white. If you go to colder temperatures like 1600 Kelvin, you only see red or red-orange, and you can see that in a kiln here. You can use your eye as kind of a spectrometer that here this tall object could be cooler than the objects that have more yellow in them or closer to orange. Okay, so black body sources. Color vision, I didn't want to go too much into this, except, you know, we have rods and cones. We have rhodopsin, photopigments. They're proteins that respond to 3 different wavelengths. Here's the normal absorbance versus wavelength. So here's blue. So when you have blue cones in your eye, it has this sort of absorption. Green here and red here. It's kind of amazing that the absorption bands for each one of these things is fairly broad. But yet you can distinguish many, many colors. You can distinguish hundreds of colors. Like in this chromaticity diagram, came from essentially Maxwell triangle. But X is the value of red light, how much red light you have. Y, the y-axis is the amount of green light you have. And then the amount of blue light is just 1 minus X minus Y. So any color you can possibly see with your eye is located within this tongue-shaped thing. If you have 0.33, 0.33, here you have white light. Any single wavelength appears on the edge of this, okay? Whereas anything in the center of this thing is a combination of X and Y. Okay, just thought I'd throw that. Yeah, here's something interesting having to do with the photoreceptors in your eye. Let's see if we can get this. Stop sharing. This is called Fechner-Prevost colors. Can you see red here? These are just black lines on white. Can anybody see colors? Does that come across? Go back here. I mean, I see red in the center here and red band out here. Did anybody see that?
I don't think we can message publicly right now.
What's that?
I can only send messages to you privately. I can't send messages to everyone.
Oh, for the chat, right?
Yeah.
Yeah, that's right. I think I said that a long time ago. But anyway, could you see any colors when this thing was spinning?
Very faintly.
Okay, but it's just black and white, and your eye distinguishes color. Anybody think that's curious? Huh. Anyway, I thought it was quite interesting. Anyway, I think the reasoning behind the reason behind it is that these different photoreceptors have different time response. So something that's moving has a different response. So when the black and white is changing from black to white at a rapid rate, some of the colors don't respond as much. So you don't see black or white, you see something in between. You see red. Okay, shall we move along to the more physics? Yeah, hold on. Chat, I don't see chat here. Okay, never mind. Okay, in all materials, especially semiconductors, they have the following concepts for the states of electrons. You have something called a conduction band and a valence band. And the name conduction comes about just because when electrons have this energy that's related to the conduction band, they can conduct. Okay, so here's, so below you can see possible energy levels for electrons in a metal, semiconductor, and an insulator. Okay, electrons can conduct as long as they're in what we call the conduction band. And the conduction band is higher than the valence band. Electrons can move in the conduction band, but in the valence band, they're stuck to, all the electrons are stuck to their atoms, their ions, okay? But notice that there seems to be a region here that's a gap, and we call that the band gap, because we're calling these things bands, conduction band, valence band. We'll get to that, why they call it a band, but let's first get to why they call it a band gap. Okay, and quantum mechanics provides a band gap. Okay, so here's a very short summary of the Bohr model of the hydrogen atom. So if you quantize the angular momentum in an orbit in a hydrogen atom, we know that it has energy levels. You can't have this electron around the a single proton can't have energy level, any energy. It has to have a discrete energy that is in a particular, I don't know, classical orbit. And that energy we know has like a binding energy of 13 electron volts. But if you go to the second level, there's a gap in energy. Okay, so this is where you get the energy gap. It's because in atoms, the quantum mechanics tells you that you have to have quantized energy levels that are separated in energy. Okay, we call those. So you have that in atoms, and you also have that in semiconductors. Of course, in semiconductors, it's much more complicated. Let's go to this. Screen. Here we go.
Let us know about the valence band, conduction band, and forbidden energy gap. The electrons in inner shells are strongly bound to the nucleus. A band which is occupied by the valence electrons or a band having highest energy is defined as a valence band. The valence band may be partially or completely filled. This band can never be empty. In some materials, the valence electrons are loosely attached to the nucleus. Even at room temperature, some of the valence electrons can leave the valence band. These are called as free electrons. They are responsible for conduction of current in a conductor and are henceforth called as conduction electrons. The band occupied by these electrons is called a conduction band. This band may be an empty band or partially filled band. The separation between valence band and conduction band is known as forbidden energy gap. If an electron is to be transferred from valence band to conduction band, external energy is required, which is equal to the forbidden energy gap.
Okay. How are they created? Why do we call them bands? Anyway, why do we call them bands? I mean, we can see why we have an energy gap. It has to do with the quantum mechanics and quantized energy levels in atoms. Okay, why do they call them bands? That's okay. So whenever you have one atom, you have a level of the ground state. When you have two atoms and you couple them so that the electrons can, kind of interact from one atom to another, they split. And then the more atoms you have, the more levels they split into. Okay, 2 atoms, n atoms. So by the time you get 10 to the 20th atoms, you have so many states that it's a kind of a continuum. So in this valence band or conduction band, there's a continuum that the separation between energies here is very, very small. You still have this big band gap, okay, between conduction and valence band, but you have all these little splittings here. And so an electron can easily go from one to the other. In other words, another way to look at it is that an electron in a string of atoms like this can hop along and conduct, if it's in the conduction band, and go from one atom to, the other end of the sample in other atoms. Okay. So that's why they're called bands. So bands, So since electrons can move, they can have momentum. So when they have momentum, then the energy is going to depend on the momentum. And just like we learned in physics 1, p squared over 2m is the kinetic energy, or h bar k squared is over 2m is the energy. So we're using, we often plot these things in terms of what we, of k vector, momentum vector, basically. So these things are parabolas because the energy depends on k squared. So this is a parabola. This is a parabola. So electrons can have, in the conduction band, can have this energy or this energy or this energy or this energy or this energy, and they can lie along this curve. If it's at rest, it's at this energy, and as it starts moving, it has a higher kinetic energy, it has a higher momentum, which is this x-axis, and it has a higher energy, which is the y-axis. Okay. You can look at some of these things. You can find lots of information on YouTube about energy bands and structure. Anyway, so to reiterate it, to summarize it, you have momentum and energy, and so an electron in a band can have any energy that lies along this parabola. The higher the momentum, the faster it goes, and the higher energy it has. Okay. Any questions? I know these are totally new concepts to almost everybody, I imagine. I don't know, maybe you'll get a little bit of this in modern physics. Any questions before we move on? Okay, so now that we have valence band, conduction band, energy gap, we're going to use that for optical detectors and optical emitters. That's the very basis of especially optical emitters, the semiconductors. Okay, so here are a lot of semiconductors that we know of that are useful. Here's their band gaps in electron volts here, and we plot this in terms of, we call lattice constant. Lattice constant is just the kind of like the distance between atoms. It's just a way, if you didn't plot them, so you'd have to separate these some way. So we just happen to separate them by how far the atoms are apart, just so they're not on top of each other. So you can see silicon is right here. It has a band gap of about 1 electron volt. Gallium arsenide is 1.5 electron volts. Here's something very useful. Gallium nitride is way up here in the ultraviolet, right? Here's a visible spectrum. Here's infrared down here. Here's ultraviolet up here. So all these semiconductors have different band gaps. We'll come back to this. I mean, here's some of the values here. Let's take a look at this. Start.
light coming in. Now remember, each of these packets of light, each of these photons has some amount of energy. And what does it do? For the light to get absorbed, it has to interact with an electron and kick that electron up to some higher energy level. Now, remember, metals, there are all of these unoccupied states immediately above the occupied states. So it's really easy to find different electrons that will absorb into these states. And that's relatively independent of that wavelength of light, right? So if I have long wavelengths, small energies, I can still absorb them. If I have short wavelengths, high energy photons, I can absorb those as well. So metals are absorptive to light because they have all of these potential places that I can kick that energy, that electron up to, allowing it to absorb light at that particular wavelength. Now let's think about insulators, right? Insulators tend to have a very wide band gap. So when that photon comes in most cases, that photon has some specific energy and it doesn't have enough energy to excite an electron across that band gap. If the energy of the photon, so energy photon, is less than energy of the band gap, it will not be absorbed, right? And the point is, there's no available energy state for me to excite that electron up to. Because electrons can't exist within the band gap, I'm not able to absorb those photons. So most insulators have very large band gaps, and band gaps that are large enough that all of the optical frequencies of light do not have enough energy to excite an electron all the way across that band gap. In other words, the band gap of insulators or of transparent materials is greater than the energy of visible photons. What about semiconductors? So if we have something with a relatively low energy, so let's think about red light, maybe that's not enough energy to kick it up across the whole band gap and get absorbed. However, if I increase the energy, it's possible for me to cross that band gap, right? So the difference between semiconductors and insulators is that now my band gap is smaller, and so I could potentially absorb light at some wavelengths. So there are a couple of different ways.
Okay. Okay, so what that was trying to show was that an insulator, you know, like glass, you can see through it because it's not absorbing any light. On the other hand, a metal has basically no band gap, so almost all the light is absorbed in it, so you can't see through a metal. And the semiconductor is someplace in between. Some semiconductors you can see through, others you can't. And if they happen to have a band gap that lies within the visible spectrum, they will have a color. So if you looked at say zinc selenide or zinc telluride, you know, they'd have a color. They would be absorbing a lot of red, yellow, green light, but not blue. Let's see. So here's something interesting. Paint, when artists use paint called cadmium red, and those are cadmium selenide or some sort of cadmium material, cadmium telluride, cadmium selenide, cadmium sulfide, and they have a band gap that's in the red. So those colors look red. So when they mix this with an oil into a paste, they make a paint that's red, and they're called cadmium reds. And they can have a variety of different red light colors, depending on how much selenium, how much sulfur is in it. Cadmium's fairly toxic though and carcinogenic. I don't advise using it. But that's an example where, you know, band gap in the visible has a color. Okay, questions? I know that's a lot of new stuff to take in. Anyway, we're going to need the concept of band gap for light emitters and somewhat for light detectors. Questions? Okay. Okay. Band gaps are very important for detectors and emitters. So in a light detector, a photon comes in. If it's absorbed, that is, if it has energy that is larger than the band gap here, it will lose its energy, and it will transfer that energy by taking an electron from the valence band, putting it up into the conduction band. So when light comes in, it produces an electron that conducts. So this material will start conducting, and you can say light came in. Okay. Light emitters, just the opposite. You start off by putting electricity in. So electricity, instead of light coming in and raising an electron up, electricity comes in and raises an electron up to the conduction band. Then, so you put electricity in here, then when so you've lost some energy in electricity, you've gained it in the electron, but then the electron is going to fall down eventually, fall back down into the valence band. So it's going to lose its energy. So it has to give up that energy to something, and it can give it off to a photon that comes out. Okay. But in both cases, you have to have light larger than the band gap. Okay. Light in, current out. Current in, light out. That's simple. Okay, here's a detector, photodetector like the one you're going to use for your experiment this week. Okay. Okay. Remember we had holes. We haven't talked about holes yet today. Well, what about holes? Let me back up. Okay. Look over here. A photon came in. It took an electron from the valence band, put it up into the conduction band, so you have an electron that can move around. Ah, but what was left behind? A hole was left behind, and this hole can move. Okay, this hole can move. So once you've taken the electron out, you've left behind a hole. So you have a free electron and basically a free hole. Okay. That's something I should probably write down here, but anyway, that's when you create a free electron, you've also created a free hole. Okay. Creates a free electron and a hole. But what normally happens if you create an electron in a hole? Remember in the p-n junction, the electron and the hole attracted each other because they're opposite charges, and they sort of recombined and disappeared again. And you don't want that to happen. So here's a p-n junction. Here's a depletion region that we had before. Light comes in, creates an electron in a hole. And normally they would like to recombine. But now remember that inside of the depletion region, do you remember that you have an electric field? So the electric field is going to take and move the electron one way and the hole the other way. Okay, so the electric field is going to separate the two, and you need this separation. Otherwise, you're not going to make a photocell. Even though light come in is absorbed, you create electrons and holes. If they're not separated, you don't get any current from it, so you're not producing any power from a photocell, a solar cell. Okay. So the electric field in the depletion region separates the electrons from holes and sends them. So in this case, it would you would have the electron coming this way, and then it could provide some current in a device or resistor or whatever. Okay, but you need this electric field in there. Something else I can point out is that the current is proportional to the number of photons per second. So each photon produces an electron hole pair. And if that electron and hole pair can be captured, then you have a large quantum, what we call quantum efficiency. And that's why you rate a photodetector in units of amps per watt. Amps per watt. Amps of current per watt of electrical power. Optical power. Amps of current in electrical current and watts of optical power. So it's how much electricity you get out for the amount of light that you put in. And good semiconductors can be even silicon conductors can have a quantum efficiency near 1. I mean, solar cells don't, but you can buy expensive light detectors that have a quantum efficiency of about 1. For every photon comes in, you create an electron hole, but they're very expensive, and you're not going to put them on the roof of your house or someplace like that. Okay, any questions on light detectors? Light detectors. Almost all of our solar cells are made of silicon solar cells. You can make more efficient solar cells out of more exotic materials, like gallium arsenide or some of these other materials, but those are very expensive. If you want to capture light and make electricity, and you're going to send it up on a satellite, yeah, you're going to pay a whole lot of money for more efficient solar cells. So you can use something that's not silicon. It's much higher efficiency, but maybe cost 10 times more. Okay. Okay, so those were detectors. Now let's go to light sources. LEDs, light emitting diodes. And here's where the energy gap comes in. That to get a certain photon energy, to get a certain color, you want a certain band gap. So if you're going to make a if you want to make a yellow LED, you want to pick something that's like gallium phosphide. You're certainly not going to pick silicon. So for one reason, silicon and germanium are too simple, and you cannot make light sources out of them. But almost all these others you can. Okay. The first LED was made out of gallium arsenide, and it is it's in the infrared. You can't see it. That's probably what's in your clicker for your television. Okay, so the band gap of a semiconductor is approximately equal to the photon energy that's produced. So you can produce any wavelength as long as you pick the right semiconductor. It has a single color. Okay, so how do you change the color? Like gallium phosphide and gallium arsenide have these distinct photon energies. How do you get something in between? How do you get something in between? Like suppose you wanted something orange here. How do you get an orange LED? Well, you can mix these two materials. You can take out some arsenic and put in some phosphorus. And that's exactly how you do it. Or you could go up from gallium arsenide to aluminum arsenide. So then you're replacing gallium with aluminum, and you could go up in this direction. So here's an example. So you can go from the infrared wavelength to roughly a green wavelength, infrared to green, by this compound of material where you're replacing some of the phosphorus, some of the arsenic by phosphorus. And because you know the two band gaps, you can calculate what band gap you're going to need, and how much aluminum and how much arsenic and how much phosphorus you're going to need. Notice that phosphorus is X and gallium and arsenic is 1 minus X. So the total here is 1. So this is exactly how they make different colored LEDs. Is they mix some of these, they mix several of these materials, sometimes four materials to get the wavelength you need. Okay, any questions on light detectors, light emitters with semiconductors? Okay, I'm going to skip this about the ruby laser, but you can look at these very short videos on how it works. First laser was a ruby laser. Okay, a laser diode is basically an LED, but it has a what we call a resonant cavity. Resonant cavity. The first laser diode was made in 1970, and later the first visible laser diode was made, and it had 4 components in it: aluminum, gallium, indium, and phosphorus. And that put it into the red. And basically it's a PN junction of this material with some other materials that are very similar to it. But some are N-type, some are P-type, and you have a junction, PN junction. So let's take a look at this. Very short.
it's a crystal, very much like gallium arsenide, a tiny crystal with mirrors front and back, polished or cleaved, so that is a largely reflecting surface on both faces. And you pass a current through the diode, it populates the space inside the junction with electrons and holes. And these recombine and produce light, which is bounced back and forth through between the mirrors, and that inspires more electrons and holes to recombine and signals out, instead of a broad beam of spectrum of light, it concentrates at a single frequency, and all the light comes out in a very intense collimated beam.
Yeah, so the point there is an LED and a laser diode are very similar. An LED has light that comes out in a collimated beam. It comes out in a beam. I mean, it shows here that it's a beam that gets diffracted bigger, but basically you can collimate it with well, you put a lens in here, you can make it collimated, you can make the beam go miles without diverging much. Whereas an LED is basically the same, but the light comes out in almost all directions. And the reason in a laser why it comes out in a beam instead of in all directions like an LED is because you have faces here and here that are exactly parallel and polished, and so the light can bounce back and forth a number of times before it decides to come out. And by the time it comes out, all the photons are we call coherent. They're coherent not only in space, making it a parallel beam, but also they're coherent in phase. The phase of the wave is the same for all the photons running around in here. Okay, so that's basically the difference between an LED and a laser diode. Is just that you have faces that reflect light, so the light can bounce back and forth in a laser. Okay. So this is an interesting story. This is kind of the end of the near the end of the lecture today. We had CDs, compact discs, compact video discs that would hold a lot more information, and then we came to Blu-ray discs. And the reason they got better here was they could store much more information. So with a CD, you had a wavelength that was in the infrared. You could only focus the beam to a certain diameter, so you couldn't get much. You couldn't make the pits any smaller. Then you can in DVD, you had a laser that was in the red, and so you can focus the red down to a smaller size because it has a shorter wavelength. I mean, here's the formula here. So if you take a laser beam and a lens, you can focus it down to what's called a diffraction limited diameter, and it's proportional to the wavelength. So that the area of the beam goes as the wavelength squared. So then you could go to smaller pits on a DVD. Then along came the blue laser, and you could has a shorter wavelength, 400 nanometers, and you could make it you could focus it very small, so you could make these pits very small. Okay, that was kind of difficult to get blue light. And there's a story about it. Okay, let me go back a couple slides. Okay, so All the lasers up until recently were in this region here. Nothing in the blue or in the UV. But now people could make nitride semiconductors, indium nitride, gallium nitride, so they could span anything in this region. So they could get blue, they could get ultraviolet. That was very important. Okay, it's very important. So the Blu-ray had to wait until you could get a small, inexpensive blue laser that you could focus very tightly to get much higher density in Blu-ray. So you could hold many movies in a Blu-ray disc, not just one movie. Okay, well, this is connected to that. Okay, evolution of light. Okay, primitive people, animals, plants only had the sun. Then humans figured out how to use fire. They could see at night. Then you had oil lamps. Then you had kerosene lamps. Then you had the Edison light bulb, and the Edison light bulb didn't change much. Then along came the compact fluorescent lamp, and then LED light bulbs. So white light requires red, green, and blue colors. The blue color didn't come about until 1990s. And you could finally make a blue LED. So once you could do that, you could take these three colors, combine them, and make white light, and make an LED light. Okay, so you need blue. LEDs are more efficient and they last longer. So when you look at a light bulb lasts like 10,000 hours. No, a light bulb lasts about 1,000 hours. Compact fluorescent lasts about 10,000 hours. And an LED lasts about 100,000 hours. So the longevity went way up, going from basically the Edison light bulb, the compact fluorescent, to LEDs. And they're more efficient. So here's the efficiency in lumens. Lumens is the amount of light that it puts out. Watts is the amount of electrical power you put in. But here's an LED. Here's LED, and they range, this kind of efficiency is averaging about 70%, 75%, where compact fluorescents are here. And incandescent bulbs are very inefficient because almost all the light comes out as heat. The light is infrared and it's just heat. You can't see it, but it warms things. So this is the progress that we've made just within certainly my lifetime, your parents' lifetime. Okay, and so all of these things these LEDs have semiconductors and PN junctions. So let's take a look at this video.
This year's Nobel Prize in Physics has been awarded to 3 scientists for an invention that has started to reshape how we light our lives, the blue LED. The prize was awarded to a trio of Japanese scientists who in the 1990s developed the blue LED, which when combined with red and green LEDs led to white LED light. That enabled the use of LED lighting to light homes, which could greatly reduce energy consumption. as LED lights last much longer and are much more efficient than traditional light bulbs. The initial invention of the high brightness blue LED is credited to Professor Shuji Nakamura, who developed it at Nichia Corporation in Japan, one of the world's largest manufacturers of LED lights. That invention was preceded by fellow laureates Isamu Akasaki and Hiroshi Amano's invention of the original non-high brightness blue LED at Nagoya University. Nakamura's compensation for his invention led to a legal conflict with Nichia Corporation, which was ultimately forced to pay him some $8.1 million in compensation back in 2005. Nakamura eventually left Japan and gained American citizenship, which led a number of American outlets to describe the prize's announcement Tuesday like this.
The Nobel Prize in Physics has been awarded this morning. It's gone to 2 Japanese and 1 American scientist.
An American scientist is among the recipients of this year's Nobel Prize in Physics.
While we're not disputing the fact that Nakamura is an American citizen, outlets seemed pretty eager to claim him as such, neglecting the fact that Nakamura has spent almost all his life in Japan, where he created his award-winning invention. Anyway, if you need proof of the wide reach of Nakamura's invention and you have a smartphone, the light it uses as a flash for your pictures or as a flashlight comes from that combination of red, blue, and green light. Nakamura, Amano, and Asaki will share the $1.1 million prize. For Newsy, I'm Sebastián Martínez.
Okay, the story behind that is the following, that when he worked for Nichia in Japan, he convinced his bosses that he was interested in making gallium indium nitride to try to make a blue LED. And so he found some people in Florida that were working on making this material. So he convinced his bosses that he should go over there and learn their techniques to make this material. And then he went back to Japan, and finally they turned that into a product. And the reason he sued the company was because he did not have a PhD, and because of the scientific culture, he could not rise above to the level of anybody who had a PhD. So basically, he sued the company because he didn't get any compensation for it. I guess he won that. Anyway, it's an interesting story. Questions? We're just about the end of this part of the end of this lecture, and then we'll talk about the experiments you'll do this week. Questions? Okay, so in the experiment this week, you're going to measure the IV current voltage characteristics of a red and blue LEDs. You've already measured the IV characteristic of a silicon photodiode, so you're going to measure these IV characteristics of these light emitting diodes. Then you're going to use this silicon photodetector. And because it's a current device, because it puts out an electron of current for every photon, you have to change that current into a voltage. And by putting current through a resistor, that changes the current into a voltage that you can measure. So you're gonna find out where the linear response is. Like if you change the light by 10%, you want the current to change 10%. But if you have too much light, it won't be linear. If you change the current by 10%, maybe the electricity only changes by 1%. In a lot of cases, you don't want that. And then in the final part of it, you're going to couple the LED. You're going to put a sawtooth wave on the LED to pulse it, and that light is going to go into the photodiode, and you're going to measure it on the scope. Okay, so just that simple. Okay, but there's a fair amount of data to plot. Okay, so that's it for today. And I'll put the notes on the link on the website. Any questions?
No, thank you.
Okay. Good luck on Thursday and Friday.